Latin, histology, Greek, MRI, and acronym. Really, the only proper English word here is a conjunction. So I decided to add a subtitle to my talk, and it's called 5 Stages of Scientific Grief, because I think it's very difficult in the 10, 15 minutes I have to distill the essence of in vivo histology, which is trying to characterize tissue microstructure non-invasively. But what I would like to do is outline the promise and the challenges of the field by focusing on a very particular research question. And basically, I will outline the stages that we went through in answering that research question. So the stages are here, and you might have seen them. They're usually used to describe the way of people dealing with grief. And believe me, this project has caused us a lot of grief. And the grief didn't really come from outside. Most of it is from within, from very critical collaborators, from long monologues in the night, and sometimes a very overzealous reviewer or conference attendee. But let me set up the stage first. This is a white matter model. We have axons in blue, we have myelin in red, and I will define 2 quantities for you. One is the myelin volume fraction, which is how much of this voxel here is red. And the other is the fiber volume fraction, which is how much of this voxel is either red or blue. And now we'll define a quantity called the myelin G ratio. This is a fundamental property of white matter. It turns out that the G ratio is relatively constant in healthy white matter. And variations in the G ratio have been associated with very serious conditions, such as schizophrenia, multiple sclerosis, and so on. So it would be nice if we could measure this myelin G ratio. But the scale at which we're talking about is micrometers. These axons are about 2 to 10 micrometers in diameter. So the G ratio is really a very particular, very small microstructural property of white matter. And the question is, how do we go from these macrostructural properties, such as myelin and fiber content, to something as small as the G ratio? And here is a very simple formula. Well, the first time I showed this formula to a collaborator was the first stage on scientific grief. The formula is wrong. And I spent a lot of time waving my hands and explaining, but look, if the arrangement is a proper hexagon and if the circles are perfectly touching. And then I said, you know what, I'll try to derive this. And to show how simple the derivation is, I'll actually do it in Comic Sans, just to annoy those of you who hate the font. Here's a fiber volume fraction derivation. It's basically the summation of all the individual large circles, the red circles. And then the myelin volume fraction is really the fiber volume fraction, the red circles, minus the blue circles. And doing this very simple substitution, we can actually take the sum outside of the parentheses, take the ratio, and here it is, the formula for the G ratio, if we have the myelin and fiber volume fractions. Well, we published this about 4 years ago in Neuroimage. And that was a great, but of course, the reaction came, and the reaction was angry. This model is useless. How can you assume perfectly cylindrical parallel fibers? White matter is not that simple. Pathology is even more complicated than that. So the question is, when does this formula hold? I showed you it holds for this case, but it holds for arbitrary shapes. For example, we have these oblique cuts, ellipsoids, or even these completely arbitrary square-shaped fibers. The formula is still there. All we need to assume is that there's a constant ratio between the inner and the outer radius. And this needs to be instantaneous in all flip angles data. So we need concentric isomorphic shapes. But what happens if we lose some of them, if we lose some of the fibers? The formula still holds. The myelin volume fraction goes down, the fiber volume fraction goes down, but the G ratio is still the same. What if the myelin thins? Well, in that case, the myelin volume fraction goes down, the G ratio will go up. And that's an important observation because that's what we will see in demyelinating disorders. The question is, when does the formula not hold? Well, we do need to assume a uniform G ratio throughout the region of interest. And if we don't have that, then the fiber caliber will affect the measurement. The larger fibers will drive the G ratio. Here's an extreme case. We have 2 fibers, one with a G ratio of 0 and another with a G ratio of 1. Well, the average G ratio here is 0.5. But what we would end up measuring is 0.7 because it assumes that all of the myelin spreads around uniformly around all of the axons, be it one very large fibers or several small ones. So rather than calling this an average G ratio, we decided to call it an aggregate G ratio. And it's not very different from most other quantitative measurements, you do need to assume some kind of homogeneity within a particular region. Well, okay, now the bargaining part comes. The theory may be right, but MRI is a broad tool to get at this. So, your formulas might work, but how are you actually going to measure this? And the truth is that plug in here for the market and fiber functions, but we decided to go with quantitative MRI techniques because they're non-invasive. We have access to them. And there's been a lot of work done on relating the Marlin volume fraction to a couple of different MR imaging modalities, such as magnetization and transfer, Marlin water fraction. The question is a little bit hazier when we talk about fiber volume fraction. What do we use as a biomarker for the fiber volume fraction? Well, it turns out that the intuition says we should use diffusion. Diffusion is sensitive to the microstructure of the axons. But intuition is not enough. And here's a piece of software that was developed by Bob Dougherty at Stanford University. And he's a very close collaborator who made this widely available. And I would be very curious if people want to look into this deeper. The project has been sitting on the shelf for a little bit. But basically, we have this microstructural model where we can take realistic fiber shapes, fiber distributions, plug them in, and apply a wide range of diffusion sequences. And we can do, half CSF and half fiber. We can also do very dense arrangements. The simulator runs on the graphics card, so it's pretty fast. It uses the CUDA library package. But it's a little outdated because CUDA keeps getting updates and it's hard to keep up with it. There's lots of things that could be done with this simulator. In particular, we want to add arbitrary fiber shapes. We would like to talk about splay and different more complex geometries. If anybody's interested, here's a proposal for opportunity for collaboration. The code is widely available through Bob's GitHub account. Well, we use this simulator to simulate diffusion in the corpus callosum. For those of you familiar, the corpus callosum is this highly myelinated structure in the middle of the brain.
Can you go back one slide?
Yeah.
Like to just boost that. Because, here we go. Cheers.
All right. Where does that go? Twitter or?
Yeah. Cool. Brainhack EDT.
So cool. I take that as a good sign. I like that. So just got talking. Corpus callosum in the brain. Highly myelinated structure in the middle of the brain. All the fibers are perfectly, are kind of parallel. So it's a good place to apply our model. Paper from 20 years ago. Somebody went in and manually calculated the fibers and their size in 5 different regions. It's a painstaking process. But we used their data, we plugged it into the simulator, and we ended up finding a relationship between the fiber volume fraction and the fractional anisotropy. So it's a one-to-one correspondence. I can measure the fractional anisotropy, that's a diffusion property, and go across, it's a quadratic relationship, and I can infer fiber volume fraction. Keep in mind, perfectly parallel fibers. Corpus callosum, pretty much the only region where we can apply that. Well, using this, we can compute the G ratio in non-human primates, and this is when we get our heads dirty. This is corpus callosum of a macaque. The fiber volume fraction, this is from the front to the back, Jenny used to mean. The myelin volume fraction, I didn't talk about this, we can measure it. And the G ratio. Now this is a noisy measure. The resolution is 0.7 in plane. A couple of things to notice. There is a trend in the G ratio. It goes from low in the genu all the way to high in the splenium. And this has been observed in the splenium has these large superaxes that are very big and thin. So it makes sense that the G ratio is higher in the splenium. This from histology on it. And you see electron micrographs genu on the left and a splenium on the right. And again, very large fibers in the splenium, higher G ratio. That's the trend we're observing. Anecdotally, this is good, but let's be a little more systematic about it. Let's connect the axon and the myelin. And let's for 8 different regions of the corpus callosum, and let's do it 3 times, so we get 24 points. This is a single set of data, genu to splenium, and these are the G ratio measurements we get from that line. One thing to appreciate, small dynamic range, values around 0.6 to 0.7. even with that small dynamic range, we see a very statistically significant correlation. So a single monkey, but the relationship is there, and the probability that we're wrong is 100. So very likely, and it would be nice to get some patient of this, hopefully in other animal models. This is when the depression kicks in. Model seems to work closely. Really, what I would like to do is I would like to be able to do whole brain G ratio measures, and then hopefully look for particular practical clinical use. And this is where a collaborator, Jen Campbell, she's a research fellow in her lab, and she basically found a way of doing whole brain fiber volume fraction measures, a diffusion technique, not neurite orientation. No time to go to the details, but we can do whole G ratio measurements. And we've tried this in cirrhosis, which is 3 lesions here, where the signal is hyperintense. And as expected, the myelin and the fiber volume fractions in those lesions go down. So that's not surprising. But what is very interesting is the G ratio doesn't behave in a predictable way. In one of these lesions, the G ratio goes up. In the other 2, the G ratio seems to be pretty normal. Now that is an interesting observation, amplified by the fact that this lesion seems to be new, and these lesions seems to be old. So far, there hasn't been a biomarker that is sensitive and specific to the age of the lesion in MS. So even though, again, it's anecdotal, single subject, we feel like there is a clinical promise here, and now we have tools to address this. So we come to the final stage, acceptance. And this is where we're currently at. The project has been getting a lot of attention. It won a couple of awards. But we're in the process of getting it out to the public and convincing people that this is easy to try and worth the effort. So I just want to wrap up with this very impressive work by Tanguy Duval from Jullien's lab, who actually goes even further and says, rather than calculate average distributions of fibers in the voxel, we can actually do distributions of axon diameters. And this is some data that he's showing in his spinal cord. And it's very encouraging because we take this, we take a myelin measurement, we compute a G ratio. We can go pretty far from this 20-year-old painstakingly drawn hand map of the corpus callosum to something we like to call stimulated electromicrographs, where we plug in MR parameters and we can get at the microstructural level. So here's an image I ran into a couple of weeks ago, months ago. Yeah, it's true. You know, conventional MRI does have more than 50 shades of gray. As a matter of fact, how many shades it has 56 shades of gray. And the resolution is on the order of millimeters. So you take a voxel, about a millimeter big, and 8 bits deep. And from there, you want to go to microstructure on the order of micrometers. How do you do it? Well, you do it with quantitative magnetic resonance imaging. You take several of these very low-res images, you combine them in a model, you do proper histological validation, and hopefully you can get much more information than a conventional MRI could ever give. So with that, I'd like to invite you to contact me. I'd love to discuss many aspects of this project, in particular if anybody's interested in the diffusion simulator. We're very interested in using it, but it does take some wrap-up time to get there. I try to be present on Twitter, and the more I'm out there, the more interactive I'll be. And I'd like to thank my collaborators and you for the attention. Any questions now, or?
I think, you know, they're gonna have 2 food days. We're like not that many, and it seems to, you know, great pitch, and I have questions for you. And,
so the only thing is I'll have to apologize that I'll leave around today. Okay, so you know, I'll try to be here most of the day today and tomorrow. But
perfect.
I'm available. I'm in Montreal. So
Is anyone more with this? Yeah. We have to back up?
Yeah.
Yes. Okay.
We have to wait 5 seconds. If it goes by, it means we have to change now. I think we're good. All right. Then maybe I can get even fancier now and raise it and also get this. Yeah. Perfect. Okay, well, sorry for the long before, but now we're good. So what I was saying, I'm going to start with an introduction of what is diffusion MRI. It's going to be a flash course on diffusion MRI. So what is the idea? The idea here is that if you have fiber structures like this, like the nerves or also called tracts in the brain, which are elongated like this, you can apply, and those are, of course, a lot of them in gray matter, in white matter, sorry, but they're also in other tissue types. And you put magnetic field, the gradient magnetic field to different directions. Through diffusion MRI, you can get back the profile of this distribution of fibers and have an idea, for example, about the orientation of this fiber population here. So yeah, we have the scanner. We can use any standard MRI scanner to do diffusion MRI. And initially, the data look like this, and then with stronger and stronger diffusion gradients, you start losing signal, and your data start losing like that. It looks like that. But the idea is here that in the scanner, we will try to put as many graded directions as possible, and then see how much signal is being lost, and from that get back in the profile of the underlying fiber population. Here is an example. If we could measure the signal everywhere in the scanner, like in every gradient direction, then and we had a population like this, then the signal ideally would look like this. It's like a pile, and where the signal is minimum, this is where you're going to find actually the real direction of the underlying fiber population. And in this circle here, you will have the maximum values of the signal. So you would expect that the opposite would happen. So you have the maximum signal to that direction and not to that direction. But this is kind of an interesting fact with diffusion MRI. But it's difficult to work with. So what do we do? It would be great if we could actually exactly how the molecules move in that voxel, and we can have the entire PDF, the probability of every molecule moving into that direction. So let's say if we had that, we're in a voxel, and we measure, we get all the signal for that voxel, and then we have a way to get to the actual probability of the motion of the water inside that voxel. Then it would look, we get a PDF that looks like this. What is really good thing is that there is a reciprocal relation that connects the signal with the PDF, which is also called the diffusion propagator. And let's say if we have now a fiber population that looks like this, which is like a crossing of two fibers, we had a PDF looking like this, and if it was one, it would look like this. And if there was just noise or just random fibers going around, it would look like this. Now, why we don't use everywhere this thing? Well, the problem with this is that it needs a lot of measurements so that do a Fourier transform from the signal and get the PDF back. And this is actually where the history of diffusion MRI comes in place, where you have DTI, where they kind of do the minimum model you can use to study how the fibers are oriented. And then you can do the best case, which is DSI, let's say the best one, where you can actually get that PDF, but you need a lot of measurements. And you have all the in-between methods, usually called CADI, where you have your graded directions on a sphere or on multi-cells of a sphere. So you can have multi-cell or single-cell acquisitions. Now, if we assume that everywhere in the brain there are only fibers group fibers going like this, which is not the case, but it's a big assumption. Then we get what we say as DTI. This is tensor. Oh, nice. Oh, you missed that, so. No, I think this one. No, it doesn't go there. Okay, now we're switching computer. Do that. That's right. So now I can use this one. Okay. So here we were here, and the different acquisition methods, and everyone needs a different model. And here we have tensor, and you can actually get, so you assume that your PDF is just a Gaussian PDF, and then from that population, you say that, okay, I can represent now this Gaussian PDF with just an ellipsoid. Okay? And then you take the ellipsoids, you put them in every voxel, you have fields of ellipsoids, and you can get the main direction of those ellipsoids like here, and then start connecting them. Or you can calculate metrics like fractional anisotropy that speak about the shape of the tensor, how thin it is, or how fat. And then you can create some really interesting, combining the fractional anisotropy with the directions of very nice pictures like color that combine together the shape of the tensor with the direction of the tensor. However, in the brain, the crossings everywhere, 60 to 90% in white matter are crossing areas. So you really need something that can deal with crossings. And to do that, most people use orientation distribution functions. What are these? They're just projections of those PDFs on the sphere. And you can find that you can actually, you don't need to create the whole PDF. You can just go directly to that animal here. And then there is a bunch of methods that try to sharpen these ODFs to make them look like this, and be more certain about what is underlying. So unfortunately here there were some videos here, but I'm not going to see them right now. Maybe some of them. But if you start connecting from voxel to voxel, this is what's called fiber tracking. And then if you keep doing it for the whole way, you create something that's called cartography, or some people call it cartography process, and the output of these things is streamlines. It's just like curves, which approximate underlying fibers. Now, if you do that for the full brain, you start getting things like this, and then you say, "Yeah, I got it now," but no, you didn't. That's only the beginning. So you have now your full brain streamlines, and now you need to see what you're going to do with it. So one very good thing is to check with anatomy and start seeing if you get structures, you get bundles from inside those that actually look what is reported from anatomy, from histology. And then another very nice idea is to start doing statistics on those bundles. And the main technique is spectrometry. There's many things. There's apparent fiber quantification. There's a bunch of techniques. But this is critical. I think people have to really get to the data and look those cartographies and get into the data. Now, diffusion Maya, of course, is useful for a bunch of things. Like I don't need to say all of them. It's many things. But here's an interesting picture with a collaboration with one of our neurosurgeons in Sherbrooke, where here you have a tumor and it's pushing the white matter. It's called cerebral infiltration. And we can visualize it here. You can actually see the streamlines, how they kind of have being pushed by the tumor. Speaking with the neurosurgeon, he was telling us that this, even when he removes this tumor, somehow the tumor finds a way to climb those white matter to different cells that support this white matter and move to different areas and appear. So think of how important it would be if you could predict that with diffusion MRI. Now, what I didn't tell you, maybe I show you some of the results and the solution. You can have this OPF, the PDFs, all very nice. But if you actually think of the initial problem, if you take a brain, you cut it, white matter is so densely packed, it's like a completely continuous film here of tracts and nerves. And you just want to do that in vivo without touching the subject and get the actual connections where those go. And that's a difficult problem. It's a difficult problem, and there was, when this method was introduced, there was no real science to deal with this. It was just the beginning. Now it's getting better. But when I was in my PhD, I was thinking, okay, this is a difficult multidisciplinary problem. You need the feedback from the doctors, you need feedback from the engineers, computer scientists. How do you do that? How do you solve this problem? And I think the problem is not being solved just by publishing papers and just by working in small labs here and there. You need to create like something bigger. You need to create a collective mind. So here is the collective mind. It's DIPI. So DIPI is a free open source library where it welcomes everyone from everywhere in the world to contribute. And we want all expertise, and our common goal is to extend the understanding of the structural connectivity of the brain. And we have a real mission trying to do that. We want to have, we make sure that things, the code we put in, has a lot of documentation, it's clearly explained, we do a lot of testing, we have a very open license so that both academia and companies can use and go and use the diffusion MRI. And we have extreme amount of testing. Also, we depend on libraries that are also very much open and everybody can use it. So this is me doing my PhD, my supervisors, all working and writing code in DIPI. All of these guys are kind of professor level. And then these are the first code developers for different places in the world who were extremely beneficial, and they're real developers and images at the same time. And then when I moved to Sherbrooke, Maxime's Decoton lab got into DIPI, and here some of the students, you would meet them also some here these days. And then here are the new leaders of DIPI. This guy is on registration, this guy on something called MapMRI, and this woman here is on a different problem of diffusion kyptosis. You might hear this. Of course, your name here, like everyone is welcome to get involved. Now, we have all these different parts of the pipeline that all need to get into the right place. But if you ask me, what are the main components of DIPI? I would say that these 4 components. You have the reconstruction, is up to the point where we get the FA, the ODS. And we support both DDI, DSI, and HADI. We have more than 20 different reconstruction methods that we have implemented. Then we can do tracking, determination, mobility. Recently, we started also doing registration. We can do both streamline-based registration, directly registration, or image-based. And we can also do segmentation. Now, you can combine all these 2 things, tracking and registration, then do a connectivity analysis, for example, which is kind of hot these days. Here is an example of constraint spherical convolution implemented in DIPI, and here it's a HADI method to connect with the previous. And then you can get those ODFs here, and then you can get the main directions here and visualize all this in DiPy. Here is an example of registration. Just let me tell you first that this was one of the most difficult things we ever done in DiPy. Basically, there is an algorithm called symmetric normalization that you use to register non-linearly. And there is only one project that is famous for that. It's the best one. It's called ANTS, and it's made by Avance and his colleagues. So we rewrote all this thing in Python with extreme efficiency, and we have it all completely documented, very nicely done, with a beautiful API application programming interface, very beautiful code, and you should start using it. So this is the development version of the API. I need to show a video on that. Can you go and click this and go? Okay, then stay next to me then. So let me tell you, this is the static, this is the moving brain, this is the static brain, the reference, and this is the evolution. You can see how this brain will change to become this. Anyway, you get the idea. And there you can see, can I play it again? Is this one? So just play the button and then look at here. Look here. It's not playing. Yeah, you can see it. Did you see it? Try it again. Look at this, how the thermographic field. So you can use that part to kind of get all these things and do them. Anyway, let's move forward. You can go back to yeah. And then we can do also segmentation, and during this hackathon we will work on extending segmentation or your cluster streamlines, for example. And this is a nice video about that. This is streamline-based registration. Let's say you segmented some bundles from your datasets. You have like accurate fasciculums from different subsets. You can register them all together, and then do analysis on them. So use DiPy and go and discover new pathways. Like this guy here, Katani did, and he discovered a new pathway from diffusion in the MRI data. It's called the frontal as track. And I think as the methods get better and better, the more pathways being discovered that we didn't know, and it will just keep happening again and again. So how to start hacking using DiPy? Get this paper from the DiPy website. There is a link to get this paper where it explains the basics. And then you can read the tutorials here. We have more than 10 tutorials. Play with existing data. We also provide data. You can fetch data even if you have to try things. And if you're advanced, you already know how to program in Python, and you already know what is diffusion MRI, you can just focus on GitHub and start sharing and get involved. So get involved, get feedback, hack it all. And this animation that you cannot see was powered by DiPy, and so in OpenOffice favors, but thank you. I'll be here all the 2 days, and these are the 2 students here who are also DiPy people, and they'll be happy to help you with anything you need.
Thank you very much. All right, so now we're going to have a little break, about 10 minutes. You have paper, plans here. If you want to pitch a project, you have 3 minutes. You don't have to have slides. You can show your website maybe or whatever. Just register here if you present something. So we'll come back in 10 minutes for pitch for projects. And then we have open hacking most of the rest of the time. Also, just a disclaimer, we had a lot of technical difficulties. I have to say that the other sites are worse. Most of them are not even able to stream, and those we do have that like nightmarish beginning of the morning. So we're still ahead of it.
So I also have a very small announcement. If some people are interested in looking at the MRI installation here, I can organize a little tour right after the lunch. We can go to the MRI facilities, which is 50 meters from here. And we have actually a unique piece of equipment in the world, which is a new 24-channel chip. So it might be of interest for some of you. So anyway, so we can organize
a project.
Okay, so let's take your project.
Yes. Alors, ce qui se passe, parce que moi je vois que ça se fait.
I'm on holiday. From what I heard, I haven't I don't know. It's not yeah, the thing is,
Par contre, on va essayer quand même de connecter ça, c'est Moi, j'ai déjà invité
Yeah, I think there's lots of shy people. Excuse me. I think there's lots of shy people in terms of project. If you have your own project and you want to pitch it and get feedback about if you're planning an experiment or thinking to start an analysis, don't hesitate to pitch that. It's perfectly legit project, and you're going to get feedback on what is it you're planning to do and the tools you're planning to use to do it. So don't hesitate to register. It's just that the only project we have right now is current development, and I think that there are a lot of people who are there, like maybe more junior starting projects and feel they're not ready to give a talk. And but don't hesitate, go for it. It's it's a small group, and you will get feedback. Hopefully, you can also thanks. I'm glad I got to discuss on how I think where comes I've done that. I did them for FMRI. So I think you what you see. Last minute to put your name on the paper. No. Okay. That's good. Yes, so Emily?
Yeah.
Yeah. So you have Are you ready?
Yep. Okay. This project is about multimodal structural MRI analysis. And I'm a cognitive neuroscientist. And the kinds of questions we often have when we're working with structural data are first, where in the brain do two groups differ? So we're actually looking for locations in the brain. And the second thing is, where in the brain do differences correlate with some external continuous variable? Like if we give someone a cognitive task and they get a score, we want to know where in the brain is related to an increase in score. So we currently use our structural MRI data like this. We collect a bunch of different modalities, we analyze them all separately, and if we're lucky, we get papers out of them. How we currently combine our data is we just kind of look at them. We say if something happened in the gray matter, something happened nearby in the white matter, and maybe those things are related, and we just run it up in a discussion section. So we were wondering, maybe there's a more powerful way of doing this. Maybe we're actually losing information by not looking at the relationships within pixel of the different information that you get from different structural MRI modalities. So we're wondering if there's a better way of doing this. Of course there is. Lots of people have tried it. However, they tend to have very different research questions from us. What they're often doing is looking at one very large patient population, one very large healthy population, and they're looking to classify an individual brain that's coming in the clinic or whatever to see what their prognosis is or if they have a disease or not. So that's quite a different question. They're just looking at classifications. They don't necessarily care where in the brain the information is coming from, and they also tend to have very large data sets, like 800 or 1,000 or several thousand brains, whereas we tend to have 12 to 20 per group. So our goal is to increase the sensitivity of analyses by combining information across several imaging modalities. What we have so far is one prepared sample data set that you can get and play with. We happen to be looking at musicians versus non-musicians, and we also have behavioral data. We have 2.5 neuroscientists, 2 computer engineers, and some supercomputer assets. So if you're interested in joining us, please come see us. Thank you.
Yes. So you can take your 2 minutes. And actually, even if you like 3 minutes of scans, it's okay. Derek? Your slides are ready? Yeah. Well, we have the other upstairs. Okay.
All right, so I'm just bringing like a project that I'm working on now to see how people might want to use that for whatever you guys are doing. So it's a bit of web-based visualization software called the Brain Browser. And there's two parts. Basically, have Surface Viewer, so it's for surface data. It lets you just kind of visualize it and map like data to it. So this one's cortical thickness data. And Volume Viewer, which is for volumetric data. Like right now, it just supports Ning. It lets you explore your volumes online. And it's all open source. Basically, like it's a JavaScript library, open source. You stick it in your web page, and it lets you view your data remotely, and that's it.
What do you want to do with that software?
For me, I don't know. Like, I want to hear what people might want to do with it and discuss and maybe work on viewing people's data through it or
Okay, so if people are interested to have features or try it out, they can
try it out with your data. If there's something missing there that you think would be or would help you in some visualization task you have, then come see me.
Can you superimpose MRI data on the second view that you showed?
Yes.
But can you put it on a layer, like MRI or something like that?
Yes, I do. Maybe I can stay in. But yeah, no, it does support functional data as well.
And I don't, is that like a fixed interface or is that more like a series of modules we could try to build a more complicated interface?
No, this is, well, because, let me just take this.
So it's like I'm thinking of a project right before where you see model imaging, if you wanted to try to use that to assemble a viewer for a more like.
No, because maybe it's like, and I was getting into trouble with this, that people don't understand that like it's a library. It's a library sitting on a web page. And it's like, and it just helps you create this little viewing surface. So here we have this little like demo thing. It's that's stuff. So even this little thing that I just stuck in the web page just to show people how it works, that like Brain Browser is just handling like that little area that the views, so you can really just stick that in any web page. So I've had people use it, like I've used it to make these more complicated interfaces, but I've had people use it just to, let's say they put up a website and have some data they just want to show it, so you create a little panel and it's like 10 lines of code and have a little viewer up there, or you can use it to like hook it into a UI to create more complicated interactions. Yeah.
Do you upload the files that are to the server or
No.
in the browser?
It is in the browser. Like this, you can hook it up to some backend application if you want. Really, the part that Brain Browser handles is fully front end, and you either load that data over network if you want, or it uses like where you load local files from your. Sorry.
You load your main files.
Yes. Yeah, the main files require a bit of pre-processing, like I said, to get them ready, but you do load them. Like there's no, if you load them from your file system, there's no network activity. Like it goes straight into the browser.
Next one.
Yeah. I don't have it. It broke.
This guy's really is hacking without it.
So, so really, I don't know how to give this talk in 3 minutes. I've given this all kinds of, I have like 20 different presentations about the world that I live in, and I usually talk for hours and hours. But I'll try to do it in 3 minutes. And the point is that I work at the Montreal Neurological Institute, and I work with all kinds of different software. The main one that I've dedicated my existence to is something called Loris. So we've built that over many years, and essentially what I've been trying to do in recent years is to come up with solutions for brain analytics, let's call it that. But essentially the idea of using imaging data or anything related to it
and how to store it, process it, deal with it, disseminate it. So these are some you may find when you're dealing with large data or project data of any kind. And so the software we built, and there's obviously more considerations behind the scenes, but basically the softwares we built, one of them is called Loris. It's a database environment that basically houses all your data in a very simple way and bridges data from various modalities all together, whether it's behavioral data, imaging data, even genetics data these days. And so this is something that is an open source project as well. You can, it was founded and stemmed from this NIH project about 12 years ago. You can get it on GitHub. You just type in Loris in GitHub, you'll find it there. I'm going to go through this very quickly because I just want to show you where Loris is right now, but I also want to touch on another solution of piece of software where Tarek is one of the lead developers for, called CBrain. And that's essentially the second part of the equation for large data analysis. Loris being the together basically comprise the entirety of large data analysis that we've created. And this is kind of a depiction of how data flows in Loris. And if I just, here's an image of the interface. It keeps updating. There's applications of all kinds, and I will skip through a lot of this. Oh yeah, this is something that got a lot of buzz recently. Oops. The Big Brain project, it's also housed in Loris, for example. It's the highest resolution data, 3D rendering of a data set ever created. So that's in Loris. And then there's CBrain, which is the other part that I was telling you about, and that's something that might be useful to the community at large. That's also going to be going open source in the beginning of 2015. So for some of you, you might already be using it, but it's available potentially to you as a complete solution for image processing. So I'll leave it at that. I won't go through too much. See, I told you I can't do this in 3 minutes. But if anyone has any questions, come see me. I'll be around here all day today, and I won't be here tomorrow because I'm running a marathon. So, I figure that's a good excuse. Anyway, that's all I have to say. So thanks.
Sneer, all there's like people can. That's 3 minutes. That's good. How do you think that people can like engage with that platform in the next 24 hours? Just like checking out how it works.
Check out how it works. If you have, like, some people here have actually even approached me. They have a project and they want to house it. Even a small one. Some people have like 50 subjects or 10 subjects, whatever it is, and they want to store it in a nice database somewhere so they can engage that way. We have all kinds of modules that we've created and maybe will create. So if people have ideas for things to incorporate, like for example, we've incorporated Brain Browser into Loris just to use it for visualization. If people have little tools or modules they want to put together, a big buzzword today is something called interoperability and data harmonization. So I've been talking with like the NiPi guys, and everyone all over the world. There's all kinds of groups that want to plug in. They have some software and they want to just join to this infrastructure. So if you are someone like that, then just also come talk to me. We can always discuss how this might work together. So that's sort of how I think Loris or even CBrain could work in this context. Any other questions? All righty then.
Alright. So I'm going to try to use a real computer with a Mac adapter, and we'll see what happens. I'm really curious. Here we go. So mini display ports are not just for Mac. Just to let you know. So I and other people working with me were working on a toolbox that's called Naya. And that thing is meant to analyze functional MRI data. It's a small project. I studied it really as a support for my postdoc work. When I transitioned and established the lab, we studied adding features, and now it's at the point where we can cover a lot of analysis that are offered in other packages, but it has also pretty unique features. So we think it's time to make it clean and usable outside of the lab. So we want to work on that. I came with several students are working with me, and we're going to try to document it better so that people that know us are able to do something with that software. So currently it looks like that, the documentation, so still on the tree. And I love that page because I think it's almost like one of the worst web page ever. First there's a color scheme, it's like this yellow and orange, like I really don't know what was gathered in mind, and then you have like this menu here, and don't get like full, this has nothing to do with the toolbox. It's Nitri, all those logos are for Nitri. Actually what matters is that on the left, on that page, you have to click on MediaWiki, because why not? You know, like you're a user, you know you have to click on MediaWiki, and then you get where you have the actual stuff, right? And here it's fairly reasonable, but really you have to forget everything you're shown and concentrate in the middle. And then you have some documentation that we, and also the site is not responsive at all. So you have some documentation that describes all the I know, but I mean that's just at the end of the day, that the feedback I get about it, you know. Then finally you reach the documentation. So I don't think this is a really practical way. So we designed it with a framework called FlatDoc. So it looks like that. So you have like, you know, how to install the stuff here. So you have a small description. You have the list of pipelines here. But we have to add things. You have a big download button, so if you want to download it, you don't ask for it for 15 minutes. And what's neat with that framework is like if on your phone, it's going to look like that because the resolution is small. But if you have a bigger screen, you're going to have like a little thing to navigate the documentation. If you have actually a very large screen, then you're going to get the code is going to be on the side, so you have really like the documentation you can read, and then all the examples are gonna get on the side. So anyway, I think it looks clean, and we're going to work in adding pages on there. And the idea would be to try to get to something like Brainstorm, which is fantastic documentation, where you have all the small tutorials, and for each task, you know that if you want to take an half an hour tutorial, you have some data and step-by-step explanation of what you have to do. So that's really what we want to get at, and some people can actually provide to follow some of the tutorials we've been working on, or like install the software. It would be very interesting to hear what they have to say in terms of the quality of the document and actually manage to get anything done. So anyway, thanks. Yeah, you just
I posted the project on the website.
Yeah, you just okay. The only the only thing is like my keyboard is not my keyboard. That's very confusing for me. Like what you see is not what you get. Now you actually have a keyboard.
Oh, very good. That's interesting.
Yeah.
Yeah. So for people who want to learn diffusion MRI analysis using DivePy, it's me, Etienne, and Mark Alex here. So you can find us, and we can have this as a measure. We can try to analyze it with DivePy. And you can see here there is a very long list of tutorials. If you play with it, just start from the quick start. And also, I'm going to go also, we're going to work on a small project today, which is on this problem of clustering and segmenting structures like this one. This is an example that is an algorithm already existing. We'll try to make it better. And here is how a cluster result looks like, but we want to make it more general and also make visualization a bit better. So if you have ideas, you can also join us. So that's it.
So I'm going to use my keyboard. Okay, so I haven't found the appropriate T-shirt, but I'm going to talk about spinal cord actually. So we have developed for the past 2 years in the lab the spinal cord toolbox, which is a collection of tools dedicated to the spinal cord, because everyone in the room is always thinking about the brain, but you know, if you extend this a little bit, you have a very important feature. Why did we want to do that? Because you know, all the repression and the susceptibility of corrections and things that have been developed for the brain don't work as well in the spinal cord. So that was the main motivation. So we did a quick a poll on about 100 of people, and so that helped us direct, you know, the tools and the language we wanted to use. So we focused on Nifty, and we also used the Python with all the libraries that LF was talking about. So I'm just going to do a yeah, sure. So this is actually, I have to say that this is.
You must choose. You go from 20% Python.
Yeah, I know.
You had some bias.
Yeah, you have to see
the future.
Yeah, exactly. So just a really quick overview. So first thing we wanted to focus the template, because as you know, there is no template for the brain. We were missing a template for the spinal cord. So with the help of people at the MNI and Marseille, we have developed the first template of the spinal cord. So it's a very exciting work. We have also created the probabilistic atlas of the white that is merged with this template, and we also made an atlas of the white matter. So we have a couple of tracks, such as the corticospinal tracks and other tracks that we can that are not and all the metrics. So it's a very neat feature. Benjamin, who is the crazy guy somewhere in the room, also developed a very useful automated segmentation software for the spinal cord. So it's very quick and it's very robust. So it can help segment the spinal cord in a very reproducible way. So that's all in the toolbox. Also, we have an extensive framework to actually register your data, just TTI and all the data to the template. So you get the anatomical, you straighten the spinal cord, you get the working fields, and then you use those working fields to actually do a two-stage registration, and then work all the template objects into your metric, and from there you can use the atlas and extract the metrics from the tracks you're interested in. So some funny features such as smoothing along the spinal cord. Not sure why is that useful for, but maybe one day someone will find a use of that. An interesting feature that we've been working on very recently is actually the motion correction is a nightmare for everyone who is doing fMRI and DTI, and for you all know about that. It's very difficult to correct for the motions. One trick in the spinal cord is that the motion is actually non-rigid. The reason why it is non-rigid is because the lungs are filled with oxygen. Oxygen is paramagnetic, and paramagnetism, as you know, shifts the frequency of the magnetic field. So if you do EPI readout, you will end up with a shift in the anterior-posterior direction, the phase encoding direction, right? So this effect has been observed at 7 Tesla in the brain, and at 3 Tesla we observed a pretty strong problem. So only because of the change of the V0 field, you can get a shift of your EPI data by 1 centimeter, which is the diameter of the span cord, right? So what we've implemented with the current version with Brain Advance is actually slice-wide registration that is constrained along the Z direction. So we basically implemented that in ANTS. So it's a new feature of ANTS for about 3 weeks now. So you can all have access to that. You'll have access to the slides, so I'm not going to describe this, but we spent a lot of time about the testing. So that was the work of Augustin, who is there. So testing procedures, and also we've used SourceForge for the binaries and for the package. NightClick as well, so we don't use NightClick for the reason that Pierre mentioned before. And all is on the GitHub as well. So just a little, so the main contributors are the Poly, MNI, and XMRC University. And I'm just going to do a very quick overview of, so similar to what Pierre showed, but on the SourceForge website now. So basically, if you go to SourceForge, you see there's I think there's even more ads and commercials and things like that compared to. So that's pretty messy as well. If you want to get rid of the ads, you can actually create a name. So there's the notation. Also, sometimes it's as responsive as the GitHub website. But what I wanted to show you is just the getting started. So if you want to play with the toolbox, we made a little batch, and you can just copy paste everything on your terminal, and it will download data, and it will, basically go navigate through the folders, and it will do, typical analysis using T2, T1, diffusion MRI, magnetization transfer, and fMRI. So you can play with it and feel free to ask questions. We'll be around. Thank you.
On a un talk. Avant qu'on démarre les sessions de travail ouvert, comme pas tout le monde a présenté ou fait partie du... Moi, je propose, c'était Julien, qu'on fasse un petit tour à la fin. Chacun qui... Hein? Oh, yeah, sorry. So because not everybody talk, what I suggest that we finish this talk session by everybody saying his name and 3 words displaying your interest, so at least we know where you're coming from before we split into groups. So you have 5 minutes to think about your 3 keywords, right?
Someone has a bag full of adapters.
Licenses. We have a poll about the language. Yeah, and it's protest. You can get 3 keywords in your language.
So we have Philippe, yes, who is going to present Atelier MATLAB 2014.
So a few maybe warnings. This first, in French, I can talk in English, I don't mind. Another warning is that people have been talking about frontiers and neurosciences. I won't talk about frontiers, rather I'll describe a project I have about just training on basic and maybe less basic coding for members of the institute here in particular, but we're open to maybe discuss about having other people. So it's not a very much a frontier in psychology or in neurosciences. And also the jokes on me, it's about MATLAB and not the much better Python. However, I think, yeah, that's great. Yes. Okay, so and what I'll present, I guess, is not the whole project, but also more in particular a survey we've done with members at the institute just to know better about what they're. Yeah.
Can you present
Yeah,
the
yeah.
slides? Yeah, I see that they're gonna.
Yeah. And I'll hold the computer this way. All right, but so we've done a survey, and basically we're asking what do people need and what would they appreciate as that training. 32 people answered, and so yeah, all of them were interested. There's at least 32 people that want to have okay, so it's people from different levels in the institute here, so both students but also researchers and postdocs. However, there was very few advanced users that answered to the survey, and basically nobody, and only 3 people, and these advanced users wanted to be part of an organization, and no people wanted to be part of a training class. So I guess since some of you might have experience with MATLAB, that could be of interest. So also how the training would happen is I was thinking about like having advanced user present the code and maybe introduce with an existing code which is being used in maybe neural analysis or behavioral analysis, and present what they've done, and maybe just open with an exercise based on that. So can you try to reproduce part of it, or can you extend on something, and have just a collaborative a period after that to have more advanced user, maybe help new user. Also, and finally, this training would take place in 2 days. So if you're interested, it could be very, and the 2 days would be very different. On the initial day, we invite only total people that don't know anything or know very little about programming, and we discuss some very simple functions and principles in programming. Whereas the other day, we'd be more open to all users, and including advanced user. And on these sessions, it'd be more interesting to present advanced script and open discussions or on an exercise for the people. I don't have much. So if you're interested in to maybe participating in the organization, maybe you figure out that it's still very flexible, being not very much advanced in the preparation. So there's place for organizing some more. Also for training, of course, if some more advanced people. I think it's a very simple task to present, because I'd like to ask a person to present like one script in a 5 or 10 minutes presentation, and then open on something else. So I think it's a minimal involvement, but I'd like different people to do this minimal involvement.
So do you like to picture ideas for exercise?
So yeah, maybe it's not something we're going to finish over the weekend, but maybe just contact us either at my email, which is Philippe Saucier, or there's also a more official email address for the MIC, so methodology and method en imagerie cérébrale or brain imaging methodology, which is a committee on site here. So you can either write to either address and pitch in a script and yeah. Ça va? Yes.
All right. So one name, 3 keywords.
Giovanni, computer and software engineering.
Emily, auditory cognitive neuroscience.
Tarek, not a neurologist.
And Zeus, diffusion MRI. Python. Oh yeah.
There's a Nicola, violin, histology, MRI.
Benjamin, MRI, and
Oh.
So Julia, more physics, Python, and it's a simple MRI.
Okay, conclude. Streamline clustering, machine learning, and Python.
Jason Stepner, neuroimaging, cognition, aging.
Tyler, dementia neuroimaging analysis.
Mom, computer engineering and AI. Hillary, cognitive neuroscience and Python.
Tina, JavaScript, PHP, and R.
Yeah, translate MRI, listening state MRI, and yeah.
And Angela and my favorite things are Wednesday, autonomous views,
And patterns.
That's based on MRI also. Yeah. And some of those abstraction, autism, clustering, some aging, and communication.
Samir, computing science, imaging, and party.
Philippe, basic functional analysis, but also chunking detection and more tapping tasks. Serial task.
Alzheimer's MRI. It's also prediction of then it's words. There are one with Yang, structural MRI, depression, suicide. That's sort of
What do you do for work?
So I have to be the party guy. And so I'm chair fMRI, hackathon, and Alzheimer's disease. I think. Okay, so I think everybody got introduced. So now we have more. So you you have the space around. There's going to be pizza around noon. It will be on the 5th floor, so we'll come get you to move to the space where we'll have a lunch and just enjoy.
Ouais, c'est ça, c'est mieux pour nous. Ouais, là, c'est se sentir
use that
It's fun. Or should I give you some
that logo, you know that the logo was like and people might and then they were more straight from and then that's just
Which one work on
kind of
Yeah, I think they try to implement something.
I don't know if you put it so
Okay, so if you want Oh no, I said this video since it's about
well, the space of the
Can you draw? You can draw. I saw you draw. I have a product. Am I making this? You guys sign up for something. I thought you also. Oh no, I think what I'm confusing is your kitchen activities. So I kind of screwed it. Can you draw on that quality? Oh, that's good. Well, so you can yeah. Good. And just ask for like share how to approach. You can always say, for those things, I'm not sure, maybe I'm going to do that. You guys have ideas about that. And then people are going to come to you to engage in your project. If you haven't done anything that we have interested, I would say, you don't know how to approach it. You can So, and then you get you have them from the so you just do them like that. Yeah, no, it's a fun environment. You have the whole weekend, things like as a way to just like work, but also just lunch. Learn to know more about the stories, and then it's just maybe like a social experience. Like at the very minimum, that can be that, and like who knows, you may actually end up making connections. But we'll see. En fait, ça aurait été bien de faire un streaming de ce site ou de streamer. Mais ouais, mais il faut l'appeler un, je peux faire. Non, stream chez nous, comme ça, si quelqu'un. Oh, bon.
La coupe ou pas?
Ouais, non, c'est vrai que ça c'est débile de streamer à l'écran bleu.
On la rallumera à 13h30.